In this video, we'll discuss one way to evaluate the limit of some given function. The reason for that is, given a function, we want to sketch the graph. There are two properties we haven't discussed, right? One is, how do we identify the horizontal asymptote? The other one is, how do we identify the vertical asymptote? So let's see that. Recall the definition. Both asymptotes involve limit, either limit at infinity, or you have a limit at a finite. You have an infinite limit at a finite number, right? So given a function y equal to f of x, to sketch, we want to sketch the graph. To make our sketching more accurate, we want to identify the horizontal asymptote and vertical asymptote. The curve is getting closer and closer to the line, but never touch it, right? So definition for the horizontal asymptote is either you have a finite limit at infinity, or you have a finite limit at negative infinity. Either this limit reach a finite number, you get a horizontal asymptote. Now, what's the definition of vertical asymptote? Is a number x equal to a, right? Such that either x goes to a here, f of x is infinity or negative infinity, doesn't matter. It's getting closer and closer, right? Or as x goes to a on the right side, the function is infinity or negative infinity, or the function goes to a on left side, f of x equal to positive or infinity or negative infinity, right? You have a infinite limit at a number either from right, left, or both sides. Or one side infinity, the other side negative infinity. Also, you have vertical asymptote. Horizontal is the limit at infinity. X is getting larger and larger positively without bound, or x is getting larger and larger negatively without bound, right? So both asymptotes involve limit, right? So this is the reason we introduce another technique, which is called L'Hopital's rule, which help us to identify what's the limit of this function at a number or at infinity or negative infinity, right? Okay, let's see that. So let's try to introduce a few indeterminate form, right? So if you have f of x goes to 0, g of x also goes to 0, right? And as x goes to a, could be a plus or a minus or infinity or negative infinity. It doesn't matter. It could, as long as you just try to evaluate a limit, right? Then if you want to calculate this limit of their quotient as x goes to a, f of x over g of x, right? You cannot plug in a, because if you plug in a, you get 0 over 0. So this is undeterminate, right? So this is undeterminate form. It could be infinity, could be 0, could be anything, right? 0 over 0. So 0 over 0 just means you have a special kind of a limit. It's a fraction, and both numerator and denominator goes to 0. And so let's see let's see what's the L'Hopital's rule, right? So let's see how do we do that. If you cannot plug in A, and sometimes, as I recalled, the derivative should be easier, right? So let's try to make a connection with the derivative of the quotient. No, the quotient of derivative, right? So let's try to justify our formula here, right? So let's assume f of a equal to g of a equal to 0, right? And f prime of a, g prime of a exists, and g prime of a is not 0. So this is our assumption, but even this assumption doesn't hold, you can still do that. Still apply the rule if you have 0 over 0, right? So we want to evaluate as x goes to a, f of x over g of x. So this part is a discussion of L'Hopital's rule. How do we get L'Hopital's rule, right? So by our discussion, because f of a equal to g of a, which is 0, so this is same as x goes to a, f of x minus f of a over g of x minus g of a, right? So that's true because f of a, g of a are 0, just subtract 0. And now try to make a common denominator, which is just to try to divide, because as I always mentioned, we want to get derivative involved. Divide by x minus a, right? G of x minus g of a over x minus a, right? Now you can see that because g prime of a, l prime of a exist, right? Both numerator and denominator have a limit, right? As x goes to a here, you can split it because the denominator limit is not 0. And by the limit laws, you can evaluate the limit of numerator and the limit of denominator, then do a quotient. So this is same as f prime of a over g prime of a, right? So this is basically the idea. So apply the idea to our formula. So this can equal to as x goes to a, f prime of x over g prime of x if the limit on if the limit exists. If you have a limit which exists, you can, if you don't know how to evaluate the limit of this, but you can differentiate numerator and differentiate denominator separately. Do not use quotient rule, right? And take a quotient, you will get an easier function, right? Then maybe after you take a derivative, if you plug a into the denominator, you do not have 0 anymore, right? Just plugging a, you get the limit of this fraction. And same thing happens if you have f of x goes to infinity or negative infinity. G of x goes to infinity or negative infinity as x goes to a, or same thing happens for a plus, a minus, positive infinity or negative infinity, right? So we get our undeterminate form, which is infinity over infinity, because 1 over 0, we know that's infinity, right? And these two are very closely related. In this case, we have that as x goes to a here, f of x over g of x. So this equal to as x goes to a, f prime of x over g prime of x if the limit exists. This is the L'Hopital's rule. So whenever you have 0 over 0 or infinity over infinity, you can evaluate the limit of f prime over g prime if the limit exists. If the limit doesn't exist, then this fails, right? So let me write down the L'Hopital's rule as a single result. So L'Hopital's rule, right? You have either 0 over 0 or infinity over infinity. So remember, infinity could be positive infinity or negative infinity. It doesn't matter positive or negative. You can just put a negative in front, right? So then as x goes to a, f of x over g of x. So this is equal to as x goes to a, f prime of x over g prime of x, provided the limit exists, right? If the limit exists, you can do that. And for sure, g prime of x is not 0 near a, right? So if you have 0 over 0, then right, this doesn't work. Okay, we cannot divide things by 0. So let's see a quick example to finish our discussion in this video. Let's see a quick example. Let's see what's the limit as x goes to infinity, e to x over 1 minus e to x, right? I can see that as x goes to infinity, right? E to x goes to infinity. 1 minus e to x goes to negative infinity, right? Because negative e to x will go to negative e to x goes to negative infinity. Then negative infinity plus a number is still negative infinity, right? Because that number is finite number. So there are some determined limit. For example, infinity 1 over infinity is 0. Infinity plus any finite number is infinity. Infinity plus another infinity is infinity, right? That's determined limit. But 0 over 0, infinity over infinity, or infinity minus infinity, we have several undeterminate forms. So this is clearly infinity over infinity, actually infinity over negative infinity, but infinity over infinity including the case any possible negative or positive infinity, right? So we apply the L'Hopital's rule. So this is same as x goes to infinity, the duality of the numerator over the duality of the denominator, right? So this is same as x goes to infinity, e to x over negative e to x, right? E to x over negative e to x, we can simplify that. That's negative 1, so the answer is negative 1, right? So this is what we are doing, right? You can see that from our discussion here, our one more conclusion here is y equal to negative 1 is a horizontal asymptote of f of x equal to e to x over 1 minus e to x, right? You have a better understanding of this function e to x over 1 minus e to x by looking at the limit at infinity, right? The limit at negative infinity will be 0, 0, right? So that's you can just plug in negative infinity. And